Hello, future engineers. This is part 4 of 2D rigid body equilibrium, levels 31 to 40 problems. Neglecting friction, determine the tension in cable ABD and the reaction at C when theta is 60 degrees. So we denote the tension in the cable, which is the same as T, as shown in the figure. Then, because theta is 60 degrees, so these are the reaction components at C, and theta is 60 degrees. So if we extend so that because this is 90 degrees, so this distance is A, this is 60, so A cosine 60, this is 0.5A. So that moment arm of T from C is 2A plus 0.5A, so 2.5A. So equation moment at C is 0, or summation moment about C is 0, or the resultant, so counterclockwise positive. So T times 2A plus 0.5A, so 2T times 2.5A, then minus T times A minus P times A equals 0. So if we cancel out A, then we have 1.5 T equals minus P equals 0. So that means T is P over 1.5, or T is 2/3 of P. Then that's it. For the reaction at C, R horizontal, or the horizontal component of the reaction of the resultant is 0. So it is equal to CH, then minus, because this is 60 degrees, the angle between the vertical and this normal or perpendicular to this inclined bar is also 60. So the component of D is to the left. It is T sine of 60 minus T sine 60. Substituting the value of D, which is 2/3 P, so CH is 2/3 P sine of 60 degrees. And since sine 60 is square root of 3 over 2, so CH is P square root of P divided by square root of 3. Rightward. Then R vertical component of resultant is 0, and that is equal to CV plus the vertical component of extension. Remember, this is 60 degrees, so T cosine 60 degrees plus T plus the vertical component here is T cosine of 60 degrees, then minus P. So C sub V is 0 equals C sub V plus 1.5 T, and T is 2/3 of P, then minus P. So C sub vertical is 0. So that means the reaction at C is just CH, and it is P over square root of 3 rightward. The portable floor crane in the automotive shop is lifting a 420-pound engine. For the position shown, compute the magnitude of the force supported by the pin at C and the oil pressure P against the 3.2-inch diameter piston of the hydraulic cylinder unit AB. So this is the figure. We have here the piston. So we have pin C here. So we will denote the force in this piston here as F, and this distance, the weight for 20 pounds. This distance is 18 inches sine of 30 degrees, so that's 9 inches. The horizontal distance is 18 cosine of 30, square root of 3 over 2 cosine 30, so this is 9 square root of 3 inches. So the angle that F makes with the vertical is inverse tangent of this distance, which is 9 square root of 3 over 6. Use your calculator there. Inverse tangent of, in the numerator, 9 square root of 3 minus 6. In the denominator, 30 plus 9, or 39. So that's 13.81 degrees. So there are two components, vertical and horizontal. So the reactions at C, leftward and let us say downward. So moment at C is 0 for solution. So counterclockwise positive. The vertical component of F is F cosine 13.81. The moment arm is 9 square root of 3. So F cosine 13.81 degrees times 9 square root of 3. The horizontal component is clockwise. So minus F sine 13.81 times 9. Then minus 420. This distance is 18 plus 42, 60 inches. That's 30 degrees. So 18 cosine 30. So this is 18 cosine 30 minus 420 times quantity 60 cosine of 30. 18 plus 42 is 60, so 60 cosine of 30. So from there we can solve for F, 1680 pounds, and the pressure here in the cylinder is force over area, so 1680 pounds divided by pi radius. Half of 3.2 is 1.6. So 1680 over pi, 1.6 inch quantity square. So that would be in pounds per square inch, or PSI. 208.9 PSI. And the magnitude of the force supported by pin C, so let's solve for CH and CV. Our horizontal component of resultant is 0, and that is the considering positive first. F sine of 13.81, where F is 1680, then sine of 13.81 rightward, then minus CH. So therefore CH is 1680 sine 13.81, so 401 pounds leftward. R vertical is 0 also. The vertical component of the resultant is 0. Let's begin with positive component. So F cosine of 13.81, 1680 cosine of 13.81 minus 420, then minus C sub V. So C sub V is 1680 cosine 13.81 minus 420, and that is equal to 1211.4 pounds. Therefore, the magnitude of the resultant at C, R sub C, is square root of 401 square plus 1211.4 square. So the magnitude of the force supported by pin C, or R sub C, is equal to 1276 pounds. The self-regulating flat gate ABC pinned at B is pressed against the lip of the spillway at C by the action of the 3645-pound weight A. If the gate is too open when the water level reaches a height h 6 feet, determine the distance x locating the weight A. Neglect the weight of the gate. So this is the pressure diagram. Only the upper part of the pressure will push this gate here. So the lower part will have no effect because it pushes this dam portion. So we are given this pressure here, 320 H pound per foot, but up to this level here, it is only 320 times the value of H up to this level. So if H is 6 feet and this is 3 feet, so that means up to sea level, it is only 3 feet. So 320 times 3 feet is 960 pounds per foot. So that's the magnitude there, and we will only consider this part. We will call the equivalent force as F, and it acts 1/3 of the remaining height here, which is 3 feet. 1/3 of 3 is 1 foot. So that means this is 1 foot. And since this is 6 feet, the distance of F from pin B is 6 minus 1, so 5 feet. And since the weight is 3645, moment B is 0. And these are the component reactions, which are not important because we only want to find x. So moment B is 0 considering counterclockwise positive, so 3645 times x, then minus F times 5. Those are the only forces involved. So x therefore is 5F over 3645, where F is the area of this pressure diagram, which is triangular. And the area is 1/2 or 0.5 of 960 times, remember this is only 3 feet. So 5 of 1/2 or 0.5 of 960 base times height 3 feet. then divide by 3645. So X is 1.975 feet. A light rod AD is supported by frictionless pegs at B and C and rests against a frictionless wall at A. A vertical 120-pound force is applied at D. Determine the reactions at A, B, and C. So we have here, because these pegs are frictionless as well as the wall, so the normal reaction at A is perpendicular to the vertical, so horizontal, NA. Then the effect of this 120 force is to cause NC to be up to the left. So this is also 30 degrees, N sub C. Then B is down to the right. So that we can solve NB directly, we will call the axis of this rod as U. That's 30 degrees also. Angle that the vertical and the perpendicular to the inclined make each other, so 30 degrees, and let's call that U. So that R sub U is 0. The component of NA in the direction of U is NA cosine 30, positive. Then NB and NC are not involved, they are perpendicular to the rod. So minus the component of 120 pounds, which is 120 opposite of 30, so 120 sine of 30. So therefore NA is 120 sine 30 degrees divided by cosine 30 degrees. So NA is 69.28 pounds. And to solve for NB, we set moment at C is 0. So considering counterclockwise positive, so we have NB times 8. Then plus NA, which is 69.28, and its moment arm, which is this, is 16, 8 plus 8, 16 sine of 30. So plus 69.28 times 16 sine of 30. Then minus 120, this distance is 8, because this is 30 degrees, so 8 cosine 30. So minus 120 times 8 cosine of 30. So we can solve NB, 120 times 8 cosine 30 minus 69.28 times 16 sine 30 divided by 8. So NB is 34.64 pounds, down to the right 60 degrees with horizontal, as shown, because the angle that NB makes with horizontal is 60 degrees, because this is 30. 30 from the vertical, 60 degrees from the horizontal. Then for NC, we set NB equals 0, MB equals 0. This time counterclockwise, still positive. So N sub C times 8 plus NA, 69.28. This distance is 8 sine 30. So plus 69.28 times 8 sine 30 degrees. Then minus 120. This distance is 16 cosine of 30. This is 16 cosine of 30 because this is 30 degrees. So minus 120 times 16 cosine 30. So N sub C is 120 times 16 cosine 30 minus 69.28 times 8 sine 30 divided by 8. So NC is 173.2 pounds directed up to the left, 60 degrees with horizontal. The pin A, which connects the 200 kilogram steel beam with center of gravity at G to the vertical column, is welded both to the beam and to the column. To test the weld, the 80 kilogram man loads the beam by exerting a 300 Newton force on the rope, which passes through a hole in the beam as shown. Calculate the torque or couple M supported by the pin. So remember, this is welded, so it can resist horizontal, vertical, and moment or couple. So the man exerts 300 newtons. So this is also 300 newtons. So this is also 300 newtons. The effect is downward because for the pulley it is up. Both will be upward. So this will be the effect to the beam, downward. Then the weight of the man is 80 times 9.81. So I directly compute it. 80 times 9.81, 784.8 newtons. And the weight of the beam, 200 kilogram times 9.1. So it's at G, 1962 newtons. Then reactions at A. These are the reactions at A. So we are interested only of MA. So moment is zero in general. So moment here is zero. So therefore, counterclockwise positive, we have MA, the resisting moment at A of the weld. Then minus 1962 times 1.2 meter. Let's just use unit of Newton meter. Then plus quantity 784.8 plus 300 times 1.8, 1800 mm or 1.8 meter. Then minus 300 times 1.8 plus 0.3, 2.1. So 300 times 2.1 meter. So we can now solve MA. This, we add all this, make this positive when transposed. So MA is equal to 4937 Newton meter, and the sense is correct counterclockwise. A machine operator produces the tension T in the control rod by applying the force P to the foot pedal. Determine the largest P if the magnitude of the pin reaction at B is limited to 1.8 kilonewtons. Neglect the mass of the mechanism. So this is the given figure. So T has two components, horizontal and vertical, which is downward. So first, let's put the reactions at B, namely horizontal to the left and vertical upward. Or the magnitude of the pin reaction at B is limited to 1.8 kilonewtons, so it is 1,800. So let's put it 1,800 newtons. So first, moment at B is 0, or summation of moments at B equals 0, considering counterclockwise positive. So we have P times 150. Then the horizontal component of D passes through B. It has no moment, just the vertical. The vertical component is T sine of 25. And it is clockwise. So minus T sine 25, moment arm is 50 mm. So from here, we can express the tension in terms of P. 150 divided by 50 sine 25. So tension is 7.099 of P. Then C R horizontal equals 0. The horizontal component of the resultant is 0. So we have T cosine 25. Then minus RBH, the horizontal component of RBH, of RB. So minus RBH. So RBH is substitute T 7.099p cosine of 25 degrees. So RBH is equal to 6.434p leftward. R vertical component of resultant is 0. So we have R vertical, RB vertical, then minus P, then minus the vertical component of T, T sine 25. So RV vertical, take note that T is 7.099p. So it is equal to P plus 7.099p sine of 25 degrees. RB vertical is 4p. So RB horizontal square plus RB vertical square is equal to the magnitude of RB square. So 6.44p square plus 4p quantity square equals 1,800 square. So from there we can solve for P. P is equal to 237.6 newtons. Determine the range of allowable values of the tension in wire BD if the magnitude of the couple at the fixed support C is not to exceed 100 Newton meter. So here, so we will denote the tension in BD as T, and it has two components. This angle is arctan of 600 over 250, 67.38 degrees. Then component reactions at C. So remember that the couple 100 Newton meter may be clockwise or counterclockwise because this is just the magnitude. So let's analyze if the couple must be clockwise for maximum or minimum tension later. So let's resolve T into its components. This is T cosine 67.38 degrees rightward and the vertical component downward, T sine 67.38 degrees. So for the reactions at C, three component reactions, I will not name the horizontal and vertical. They are not important. Just the couple, which is either clockwise or counterclockwise 100 Newton meter. So for minimum tension, it should be same sense as the couple. So for minimum tension, the couple should be clockwise because the moment of this tension force will also be clockwise. So that's the idea to make tension minimum. For maximum, it should oppose the moment of the components of tension so that T will be maximum also. So idea, moment is 0, and that is at C. The resultant, so clockwise positive. So we begin with this component, T cosine 67.38 times 0.6 meter. Let's make the 600 mm to 0.6 meter so that it is consistent with this 100 Newton meter. So T is in newtons. Then plus T sine 67.38 times 0.15 meter. Then minus, this is counterclockwise, minus 450 times 0.4. Then minus 750 times 0.5. And plus 100 because for minimum T, it should have the same sense of moment of the tension. So plus 100. So from there, we can solve for T. 450 times 0.4 plus 750 times 0.5 minus 100 divided by quantity 0.6, 67.38 plus 0.15 sine of 67.38. 0.6 cosine 67.38. So T sub BD equals 1232 newtons. That's the minimum. For maximum tension, the 100 Newton couple limited moment at C, fixed support should be opposite in sense or same sense as the moments of these applied forces. So counterclockwise. So the equation is the same except that this is minus 100. So M is 0, T cosine 67.38 times 0.6 plus T sine 67.38 times 0.15 minus 450 times 0.4 minus 750 times 0.5, then minus 100. So this time T is, tension BD is 1774 newtons. Therefore, 1232 is less than equal to tension BD, and tension BD is less than equal to 1774 newtons. Level 38. The uniform bar OC of length L pivots freely about the horizontal axis through O. If the spring of modulus K is unstretched, when C is coincident with A, determine the tension T required to hold the bar in the 45-degree position shown. The diameter of the small pulley at D is negligible. So here is the given figure. So for the solution, let's have the weight because the bar has a mass of M. So it acts at the center, mg. And for the tension, we resolve this into two components, namely horizontal T sine 30 and the vertical is T cosine 30 degrees. For the distances, so by the way, the tension in the spring is K delta S. Let's solve for delta S later. Then because this is L over 2 sine 45, and of course this distance will change. So I'll call the angle that this tension in the spring makes with horizontal as theta. So therefore, this component of tension is K delta S cosine theta, and the vertical component is T delta S sine of theta. So these are the component reactions at O, which are not important. Then this distance is L sine 45, while this vertical distance is L cosine of 45. Then this is L over 2 cosine 45, because the distance from O to A is the length of the bar when C is coincident with A. Therefore, this distance is L minus L over 2 cosine of 45. While this one is, because this is the center, half of L sine 45. So L over 2 sine 45 degrees. And this is L minus L over 2 cosine of 45 degrees. Again, OA is L, the length of OC. Then minus L over 2 cosine 45. So take note that SO is 0 because it is mentioned that when C is coincident with A, the spring is unstretched. So the original length of the spring, unstretched length of the spring, is when B is here, because B is the center, it is L over 2. LO is L over 2. Then for the final length, you look at this figure, it is square root of L over 2 sine 45 degrees plus quantity L minus L over 2 cosine 45 degrees quantity square. So using the calculator, the final length of spring is 0.7368 L. Therefore, the final displacement is final length minus original length. So K delta S therefore equals K, final displacement, final length minus original length, minus original displacement with 0. So the value of K delta S therefore is equal to 0.2368 KL. So we now we'll solve for theta. Theta is arctan of L minus L over 2 cosine 45 degrees minus over. So again, theta is arctan of quantity L minus L over 2 cosine 45 over L over 2 sine 45. So imagine that L is just 1, or you can cancel L. So theta is equal to 61.325 degrees. So this is equal to 61.325 degrees. So MO equals 0, summation of moment about O equals 0, counterclockwise positive. So we have T sine 30, the moment arm is L cosine 45, plus T cosine 30, moment arm is L sine 45, that's counterclockwise. Then everything will be minus, beginning with this minus 0.2368 KL, that's K delta S, cosine of theta, where theta is 61.325 degrees. Then moment arm is L over 2 cosine 45. Then minus K delta S minus 0.2368 KL times sine of 61.325 degrees. Moment arm is L over 2 sine 45. Then minus mg times L over 2 sine of 45. Now, cosine and sine 45 are equal. Therefore, every term here has cosine or sine of 45. So we divide everything by cosine 45 or sine 45. So we ignore in the calculation cosine 45 or sine 45 here. So we compute T sine 30, cancel also L. So T sine 30 plus T cosine 30, that's 1.3660. Then combine negative 0.2368 cosine of 31.2368 KL, cosine of 61.325 degrees, then times 1/2 because we cancel cosine 45 and L. Then minus 0.2368 KL sine 61.325 degrees divided by 2 because we cancel L sine 45 also. So that would be combined value is negative 0.1607 KL. Then here it's just negative mg over 2 or negative 0.5 mg because we cancel L sine 45. So finally, T is 0.1607 KL divided by 1.366, then plus zero point 0.5 mg divided by 1.366. So the answer is T is 0.1176 KL plus 0.366 mg. So that's it for this problem. The centers of gravity of the 50 kilogram lift truck and the 120 kilogram box are at G1 and G2 respectively. The truck must be able to negotiate the 5 mm step when the pushing force P is 600 newtons. Find the smallest allowable radius of the wheel at A. Be sure to check whether the truck will tip. So this is the given figure. So for the solution, let's consider that let's solve for R when this lift truck will tip over this corner here. So if it will tip over this corner here, then there will be no reaction at A, no reaction at B because it will tip. So meaning moment at this corner here, not at A but at this corner is 0. So let's enlarge that portion. So let's apply the weight of this one at G1. 50 times 9.81 is 490.5. 120 for the box on 20 times 9.81 is 1177.2 newtons. Then P is 600, take note. So I enlarge this wheel here. So this is 5 mm, this is the reaction, and this corner I call that 0.1. So the radius is R. I'll call this distance X, and this is R minus 5, of course. So I exaggerate that when when this truck is about to negotiate this 5 mm step, then there will be no reaction at A. Same is true when it can negotiate and not by tipping. There should always be no reaction at A. Because if there is reaction at A, then it means it is still in contact with A. So how can it negotiate this 5 mm step? So that's the analysis. That's the trick in this problem here. So this problem is a star problem from Peter La's book. So M1 is 0, and our equation will just be purely moment at 1 is 0. Considering clockwise, counterclockwise, positive, so equals P times the distance is 1,200 up to center here, then plus R minus 5. That's why you have here R minus 5 because we set M1 0 here. So minus 1177.2 times this distance 1200 minus 500 is 700 up to the center. And since 0.1 is up to this corner here, so plus x. Then this distance up to A is 1200 minus 375, that's 825. So minus 490.5 times quantity 825 plus x. Then simplifying, substituting P equals 600 times 1200 minus 5 is 1195, so plus R. Then negative 1177.2 times 700, negative 490.5 times 825, that's negative 1228702.5. Negative 1177.2x and negative 490.5x is negative 1667.7x. So combining 600 times 1195 and negative 1228702.5, So we have 0 equals 600 R minus 511,702.5, then minus 1667.7x. Replacing x by square root of r squared minus quantity r minus 5 squared. So 600r minus 511,702.5 minus 167.7 square root of r squared minus quantity r minus 5 squared. And we have 600r minus 511,702.5 minus 167.7 square root of 10r minus 25, because r squared will be cancelled here. So the middle term is negative 10r times negative, so 10r. The last term is 25 or 5 square, then negative of 25 is negative 25. So by trial and error, R is 1151 mm. That's one something meter, which is very, very large wheel. So which is very big. So that should not be the answer. So tipping cannot occur. It will just negotiate by rolling up this 5 mm step. So for the second solution, let's compute for the magnitude of R1. But the analysis is when this wheel A here start to negotiate this 5 mm step, then as I said earlier, for it to negotiate, there should be no reaction at A, only at B, because this is heavy compared to the applied force. So because it will not tip also. So therefore, let's solve for NB by summing up moment about the center. I'll call this O, center of this wheel here. So that R1 and R1 is not involved because it passes through A. There should also be no reaction at A, of course, because the condition is the the smallest allowable radius of the wheel at 8 for this track to negotiate on this step. So moment at O equals 0, and that is NB times 1200 minus 1177.2 times 700. There's no more plus x because we set moment at O to 0, and R1 passes through O also. Moment of R1 is 0 also there. Then minus 490.5 times 825. So that's it. Then P is already here, plus 600, then minus 490.5 times 825. So we can solve NB equals 423.92 newtons. We then set R vertical equals 0, the vertical component of reaction 0. So we have R1 vertical equals R1 vertical plus NB, which is 423.92 minus 1177.2 minus 490.5. So RV vertical equal R1 vertical equals 1240.78 newtons. Then horizontal component of resultant is 0 also. Then this is equal to the horizontal component of R1, R1V, then minus P, which is 600. So R1 horizontal equals 600 newtons. Finally, the magnitude of R1 is square root of 600 square plus 1240.78 square. So R1 is equal to 1380.94 newtons. We then equate the vertical component of R1 to 1243.78. So the vertical component of R1 in terms of these distances is R1 times R minus 5 over R. So 1380.94 times R minus 5 over R equals 1243.78. So simplifying, 1380.94 R minus 6904.7 equals 1243.78 R. Finally, R is 6904.7 divided by quantity 1380.94 minus 1243.78. So R is 50.34 mm. The answer is the same if instead you equate the horizontal component of R1 to R1 horizontal is 1380.94 times x over r. So times x over r to 600 and replace x by square root of 10r minus 25. You will arrive at the same answer. A slender rod AB of weight W is attached to blocks A and B which move freely in the guides shown. The blocks are connected by an elastic cord that passes over a pulley at C. So part A express the tension in the cord in terms of W and theta. And part B determine the value of theta for which the tension in the cord is equal to 3W. So here is the given figure. So we will denote the tension as T in the cord. This is also T. Then NA would be rightward to oppose this tension here. And NB will be upward, of course. Then for the horizontal distance, L cosine theta. For this vertical distance, L sine theta. And the distance of weight from B is L over 2 cosine theta. So that NA and NB will not be involved in our derivation for tension T in terms of weight and theta. We extend here so that it will meet with NB, and I'll call that point O. So moment O is 0. And considering clockwise positive, so it is equal to T times L cosine theta, then minus T times L sine theta, minus W times L over 2 cosine theta. So cancel out L or divide everything by L, then factor out T for these first two terms. So 0 equals T times quantity cosine theta minus sine theta minus W cosine theta over 2. So therefore, T is W cosine theta over 2 divided by quantity cosine theta minus sine theta, so that the answer will be compact and good looking. We bring down cosine theta into the denominator and write it as W over 2 quantity cosine theta over cosine theta minus sine theta over cosine theta. So that the tension is W over 2 quantity 1 minus tangent theta. So that's the tension. Then in part B, when tension is 3W, find theta. So 3W equals W over 2 quantity 1 minus tangent theta. We cancel out W. So that means 1 minus tangent theta is 1 over 3 times 2 or 1/6. So tangent theta therefore is 5/6. So theta can now be computed. Arctan of 5/6 equals 39.81 degrees.